Okay, so we're doing exponents and logarithms. Yeah. Instead of we're doing logarithms all the time, we'll just say logs for short, just because it's a lot easier to say and it goes by a lot quicker. Again, keeping up with notes. This is number 23. Today is May 10th. Okay, so first thing we're going to do is we're going to look at some exponents when we go through these. And now with exponents, we're changing gears just a little bit because we're looking at exponential functions or exponential equations. Okay, so for exponential functions, exponential equations, they're still basically the same thing, just a little bit different when we go through these. If we're talking about exponential equation, it's y equals b to the x power. And for an exponential function, again, instead of doing y equals, it's f of x equals. All right, now the biggest change on this one, the one big difference that we have going through these is that everything we've done up to this point, we've done x squared or x to the third or the square root of x or something like that, where we've kind of reversed it around. Now instead of x being in the base, now x is in the exponent. And that's what makes these different when we go through everything that's here. So before we were doing x squared, x to the third, x to the fourth, that kind of thing, where x was the base. Now the base is going to be a number. So when we're looking at these kind of problems, it may be that we've got like y is equal to 2 to the x power. Or, if it's a function, it could be that's f of x equals, and it doesn't necessarily have to be a whole number. It could be a fraction. It could be like 1/3 to the x power. But where base is just some number. And again, now the one catch on this one is we don't use base to be 0 or 1, because if it's 0, 0 to any power is still basically just 0 for that one. Same thing if the base is 1, because if it's 1 to any power, it's just going to be 1 repeated on this one. So for all these, the base can be any number other than 0 or 1. So when we're talking about the base on these that we're going through this, just realize we're not going to use 0, we're not going to use 1, because those two things just kind of give us a problem that doesn't really have to do anything, because again, if it's 1 to a power, it just keeps repeating over and over and over and over and over for these. All right, now first thing we're going to do is we're going to back up and just do an exponential equation. Number one, it's going to just review doing exponents. Number two, we're going to do a quick graph on it. But the big thing for what we're going to do for this one is just to make sure that everybody's okay with how everything goes and what to do with exponents, because really we just need a review of numbers to powers for these. So let's do this. So we're going to do y equals, 2 to the x power. And we're just going to make a chart over here so we can go back and see what these numbers would be. Okay. And now the whole number, the positive values for x, when we plug it in, it's not going to be a big deal. It's the negative numbers that we got to go back and review, because I don't know that we've done a whole lot with the negative numbers this year. So we need to at least go back and kind of look at them just a little bit. All right. So for the first one, y is equal to 2 to the third power. Well, 2 times 2 is 4. 4 times 2 is 8. So ordered pair on that one would be at 3/8. Okay, for the next one, y is equal to, for x, 2 squared. 2 times 2 is 4. 2 to the first power is just 2. Okay, and here's the big one that you got to go back and remember. And again, I think we've talked about it once, but it's probably been a while. If you do anything to the 0 power, whether it's 2 to the 0 power or 12 to the 0 power or 42 to the 0 power, it doesn't matter what it is. There's one answer that you get from those. And I'll give you a hint. It's not 0. Anybody remember what anything to the 0 power is? Again, it's not 0. Been too long? It's going to be 1. Again, it doesn't matter whether it's 2 to the 0 power or 42 to the 0 power or 173 to the 0 power. Anything to the 0 power is 1. Because again, if you kind of stick to the pattern of what we're doing here, every time you come down a power of whatever number it is you're working with, you're basically going to divide. So this one we would divide by 2. This one we would divide by 2. And we'll still keep going here. We'll still take this number and divide it by 2. So 2 divided by 2 would make that out to be 1. So that order pair would be at 0, 1. Okay, with negatives. And again, I don't know if we've done a whole lot with negatives. So this is where we have to show you. If you do 2 to the negative 1, well, we would still do the same thing. We would still divide by 2. And if you do 1 divided by 2, well, that's just going to be a half. All right, and basically here's what it is. If you have a negative number, you can take whatever that number is and the power, everything that's here, and basically you can take this thing, the negative means it's going to be a fraction, so it's going to be 1 over, and then you can just rewrite this number like it is with the negative off of it. So it's 1 over 2 squared, but 2 squared would be 4, so that's going to be 1 over 4. Okay, and then the same thing with the negative 3. It's 2 to the negative 3 power. And here's kind of the connection you can do on these. This answer was 8 if it was 2 to the 3rd power. If we do 2 to the negative 3 power, it's going to be 1 over that answer. Just like it was 2 squared was 4. Well, if it's 2 to the negative 2, it's going to be 1 over that answer, so then it became 1, 4. So you can always pair those up. If you have a positive exponent and a negative exponent, they're the same thing. The only difference is for the positive exponent, it's going to be a whole number. If it's a negative exponent, then you make it a fraction. Again, this would still have been 2 to the 1st, so then those two are kind of together. So you can always kind of connect those two things together. The only difference between a positive exponent and a negative exponent is, again, positive stays a whole number. If it's a negative exponent, then you make it a fraction. Okay, and then last thing we'll do with this one is we're going to go ahead and graph these numbers so you can see what that would look like. Now it's not going to be like a super detailed graph. We're just going to kind of give it a rough sketch. Okay, so we start graphing these. 1, 2, 3, and we'll just kind of rough sketch these numbers a little bit so that we've got 1, 2, 3, 4. You don't have to be super detailed, just as long as we've kind of got them here. So the first point we got here was at 3, 8, so that's going to put us up here. Next point was at 2, 4, which is here. Next point is at 1, 2, which was here. And we've got 0, 1. Now, and with the fractions back here, you just have to kind of best guess it because it's going to be hard. This was at a half. This was at a fourth. This was at, and it starts getting so close to 0 that it's really hard to tell. But again, we're just kind of making sure we've got it. If you start connecting the dots on these, basically it's going to look something like that. And with an exponential graph, when you do these, this number starts to go up really fast. If anybody's taken the medical academy or anything with science, you know that if you've got some bacteria in a petri dish, or if you've got bacteria somewhere else, that once it starts to grow, until you can stop it and clean it, put something on that's going to stop it, it's just going to start growing and growing and growing like crazy. And that's kind of what we're doing here. Same thing back here on this side is that if it goes off, then it slowly, we can kind of kill it away here. Okay, so there's your basic. Now, this is because it's growing, they call this a growth. And you get a growth when your base is greater than 1. So whether this is 2 to the x, or whether that's y equals 3 to the x, or 4 to the x, or anything like that, it's all going to have that same basic shape. Now, it might be just a little bit, may not be quite as steep, or it might be a little bit more steep, just depending on the number you put in there. But whether it's 2 or 3 or 4 or 5 for your base, anything bigger than 1, it's always going to have the same basic shape to it. Maybe a little flatter, a little steeper, but overall, that's going to have that same basic shape for this one. If you do decay, well, it's just the opposite. Decay, it's going to start out high on the left side, and then eventually it's going to come and flatten back out and go this way. Now, the one thing that these two graphs have in common, this point was at 0, 1 on the y-axis. This point is also going to be at 0, 1. So if we talk about a growth and decay, that's the one thing that they always kind of have. And really what you can think about those as being is like, this is, if we talk about like real world applications in a lot of cases on these, is that you don't look at the numbers to the left of your y-axis. That this would be, all right, if you started with one something of bacteria and then you started to let it grow, then it would be this way. This would be over here if you were doing carbon-14 dating. This is where you start with 100% of the carbon-14 that's in a living organism, and then as soon as it dies, then it starts to deteriorate. So this is kind of following that deterioration pattern of how much it's decreasing as you go through those. So you'll get a decay when it's somewhere between 0 and 1, because it's a certain amount of time. It's telling you how fast or how slow this thing deteriorates based on the time that's there. That's how they use carbon-14 dating. Is they check for how much carbon-14 is in there, and they use that to kind of gauge. Now, it's not 100% accurate. It's a good guess as to what it is, because if they carbon date something that's 50 million years ago, well, there was nobody around back then to know if that's exactly when it died. So we don't know. It's a guess. It's an educated guess is when we think it happened. Exponential growth, that one's a little bit easier because this is where you start with something and then you turn around and let it go. Let it grow and let it grow and let it grow. It's not quite exponential growth, but there was a guy, it's probably been 10 years ago, started off with a red paper clip, and he wanted to see what he could keep trading to get from his red paper clip. He traded this red paper clip for like an eraser. And a lot of this he was doing it through like eBay back then, and now you can do it through all kinds of different social media, but there wasn't tons of social media back then. But anyway, he just wanted to see how far he could get trading up. He traded up to the point where I think he had a bicycle, and then some of his friends started talking, and I guess they found about it. So then they interviewed him on the news, and like he said, yeah, I started off with a red paper clip, and now I'm up to a bicycle. Well, then when people heard about it, they wanted to kind of join in too. So then people started giving him a little bit better trades because they wanted to be part of it. So eventually he got to the point to where he took the red paper clip, and after it took a while, I think after a year or maybe a couple of years, he got to the point where he had traded up to where he had an apartment paid for a year. And that's his whole thing. He said, I wanted to see how far it would go, and I wanted to see if I could get to the point where I either had a car or if I could get somebody that would give me some rent for a year, something like that. Now it went back and forth, and it made publicity, got to where people were hearing about it, so he got some better deals than he probably normally would have. But still, he started with a red paper clip and then got to the point where he paid off an apartment for a year. So that would have been exponential growth. He started off kind of small, and then eventually, once he got to the here and they got the news and they picked up on it, well, then it started to take off and grow and that kind of thing. So there's all kinds of different things you can do that. You can do money. If anybody's looked at the national debt clock, it's not quite exponential growth, but it's still got a fast growth when it's going through this thing. It would be that kind of way. Okay. The other thing, when they talk about these, whether it's growth or decay, if it's just a basic model, both of these two, your domain and range. Again, domain's your x values, so this one goes as far left as you can go. It's still going up, but it's still going to the right side also. So your domain would be negative infinity to infinity. And for your range, it's a little bit different because, again, range is up and down. Of course, it goes up forever. Same thing over here. This one goes up forever. It's back over here. It bottoms out at 0. But again, if it's decay, even in carbon-14, there's always something left. So they do 0, but they still do parentheses. So you can get really close to 0, but you don't quite get to 0. You can get almost down to nothing, but there's always a little bit of something left here. Same thing with this one. You've got to have a little bit of something here. If you've got if you're talking medical field, if you've got a completely sterile environment and you're trying to grow bacteria, you've got to introduce something on that one. So you've got to have a little bit of bacteria there to get this thing to go. If it's completely sterile, then you can't get bacteria to grow. So there's got to be at least a little bit of something there to get it going. Okay, so that's exponentials. That's what you want to kind of think about when you're looking at the numbers. Again, you've got exponential growth, you've got exponential decay, and this is just going back and picking up the basics on, what the exponents are. Of course, the positives were good. The negatives, I don't think we've done a lot with that one. And just realize that negatives, those have to be fractional answers when we go through those. Okay, so there's the basics on exponents. We're going to look at log functions and logarithmic functions. And then we'll start tying the two of those together. Okay, again, instead of saying logarithmic every time, we'll just say log for short, just because it's a lot easier to say. And doesn't matter if it's functions or equations, it's still, the same thing. Okay, so if we stick with equations, we'll just say a log equation. We'll say it's y equals log of x, and they're going to put the base down here. Okay. And b is equal to the base, just like when we're doing the exponential functions back here, that b was equal to the base. Okay, so that's the one thing that they have in common, is that they both have the bases on these together. Here's the connection for these. And they'll kind of go back and forth on these, and we'll show you how to work through these. That when we talk about log functions or log equations, that log functions and exponential functions are inverses of each other. Okay, and if you remember when we did inverse functions, it's been a few weeks ago. Big thing with inverses was, when we were working through these, is that this is where you have to switch the x and the y. The other big thing on this one that we want you to kind of think about when you're going through these is that if you have a log function and exponential function, since they're inverses, they cancel each other out. So you can think about like log functions, if this was like x squared, exponential functions would then be like square root of x, that if you put those two things together, they would cancel each other out, kind of like we were doing last week with the exponents and the radicals. And then you just get x off this thing. So that's kind of what you want to think about. If this one was a plus x, then this one's going to be a minus x. That they're always going to cancel each other out, is what it comes back to. And what it comes down to, in the real world is that, if we've got one written one way and we can't solve it, then we're going to turn around and rewrite it another way, and then they'll be able to cancel each other out. So just realize that that's kind of what they're going to do, is that logs and exponents get to cancel each other out because they're inverses. They do everything the opposite way, if you want to think about it, something like that. Okay, so first thing they're going to ask you to do, and this is where we just get some practice, is they're going to ask you to rewrite an exponential equation in log form. All right, so if we have something in the exponential form, they're going to ask us to change it and put it in log form. So this is where we're going to have to rewrite it. All right, so here's what we're going to do. We've got some exponential base that we've got here. So we're going to say b to the x power. That equals y. Okay, and for log functions, if you haven't ever noticed this on your calculator, there's a log button on your calculator. For this Texas Instrument, it's right here in the top left corner, right below the second button. If you notice, it says log right there. If you hit that button, it gives you the log part of this one. So that's what this is used for when we go through those, because it's got it right there. So to rewrite it in log form, you basically write down the word log. The base that you have here, whatever this base is, the x is here, the base will stay the same. And then here's the exponential. Here's the inverse part of it. We're switching these x's and y's that's here. So what looked like it was b to the x power, now it kind of looks like b to the y power. And the y that was by itself, well, now it's the x that's going to be by itself. Okay, so the base stays the same when you do these. So whether you go from log to exponential or exponential to log, the base is always going to be the same. Okay, so what we're going to do below that is, if you want to, below this one, you can just kind of make an X through it, or we're going to do just some examples on this one, just so you can kind of see what it looks like with some different numbers in here. So let's say you have 6 squared equals 36. And they're going to ask you to rewrite it in log form. All right, well, same thing. We're going to put the log that's here. And again, wherever you have something that's raised to a power, that number is your base, so the 6 is going to stay there. And then you just switch these two numbers. The 36 goes over here with the 6, the 2 now goes over to the right side by itself. Okay, and that's it. That's all you have to do. If they ask you just to rewrite it, that's all that you have to do, is just switch up the two numbers. Now, there's some points in times where they go through some of these, they'll ask you to solve it, but we'll do that one here in just a little bit. So for this one, we're just going to get you used to rewriting these. If it's 81 equals 3 to the 4th power. Again, we'll just write down the word log. Find out the one, it's 3 to the 4th power, so 3 is the base, so that base will stay the same here. And then you switch these two numbers. The 4 was with the 3, now the 4 goes by itself. 81 was by itself, now it goes with the 3. Okay, then they'll start throwing some variables in there. Now again, as long as we're rewriting it, you don't have to solve anything. It's just rewriting it, so it's just a matter of just getting it in the right order. And that's half the battle. If you can get it in the correct order, then we'll start showing you how to solve these and how to get through everything. All right, again, we're going to go log. Base was 13, so that'll stay the same. Again, I just switch these two numbers. The 47 will go there, and the x goes by itself. Okay, kind of going like to some review here a minute ago. If you've got something to the 0 power, that's always going to equal 1. And just to give us a different look on this one again, it's 3 to the 0 power, so your base is 3. And just switch up those two numbers. So the 1's here, and then the 0 goes there. Okay, so from exponential to log, that's all you have to do is just take whatever numbers you have, keep the base the same. Again, if they ask you to rewrite the log expression, of course, you have to write the word log. The base will stay the same, and you just switch up to the two numbers. If we do it in reverse, it's the exact same thing. We're going to take the word log out, the base will stay the same, and then you switch these two numbers. So it's always just undoing the other one, so it's the exact same thing, just in reverse order. Okay, so for these, we're going to rewrite in exponential form. And some of these, they're going to ask you to, after you rewrite this in exponential form, they're going to ask you to rewrite in exponential form and then solve. I think sometimes they may say evaluate. You know, they might say simplify. They'll basically tell you to do something else for this thing. And we'll kind of do a little bit of both. So that most of these we'll rewrite them first. Once we've got them rewritten, then we'll go back and solve it for the problem so we can kind of see what's happening with it here. Okay, now this is something I can remember when I first started doing this, because I got really confused on these when I was first time going through this one. They would give me something like this, and they'd ask us to rewrite it and then to solve it. Well, the first thing is, when I would see this one, I was like, well, how am I going to rewrite it? It's not equal to anything. So when they give you this, you basically just have to think this, that you're still going to have your log of 16 base 4. You've got to just add in that it equals X or something like that. Because they don't give you that, you have to kind of go back in and put that in yourself, which is a little bit different, because most time we're not adding different things in. But in this case, that's kind of what you have to do, is you have to almost add that in there so you can kind of see what's happening with it. All right, then once you've got it here, then you can go back and rewrite it. So if you've got a problem and you've got something like this, the easiest thing for me to do is just to write it down underneath it here. You're going to take the log away. You're going to bring the 4 down, and then you just switch the other two numbers that you have left over. Okay, so that would be your answer in exponential form. Okay, to solve it from there, then you're going to basically, it's like a second part. We've got 4 to the x equals 16. This is one that sometimes it's just a matter of kind of thinking through the numbers and figuring out what it is that they're going to be. So from here, it's just kind of going through your powers. If it was 4 to the first power, that would be 4. 4 squared would equal 16. So if 4 squared equals 16, then that means that x would have to equal 2. So they would say x equals 2. Now, the difference is they won't give you like x. This is one, if they gave you a problem like this, they would just tell you to solve it or simplify it, and they'll just give you a box, and you just go back and put 2 in for the box. But the thought process that you want to go through on that one is that if they give you something like this, and they're asking you to rewrite it or to solve it, you've got to put an equals x there. And for me, once I put that in, it made a lot more sense to me. Without putting that in there, it was just a little bit tougher to kind of think about it. sometimes I would tell people, instead of putting an X, if you want to put a question mark there, what does that equal? But if they tell you to rewrite it, then of course you need an actual value there. So again, that's what a question mark always is we're figuring out what X is. All right. So for example, 2, let's do same type thing. Let's do log of 1 with a base of 72. Okay, and again, they don't give you a value for this one, so I would say just log of 1 base 72. Just so you've got something here, you've got to kind of think about it as being equal to X. And maybe if you want to go ahead and rewrite it this way, that would be fine too. So you want to think about it this way or rewrite it this way. This is kind of the thought process you want to go through for this one. Okay, so then to rewrite an exponential, that would be 72. Take the log off, and you just switch these two numbers. So the X will go here, and then 1 goes there. So if they ask you to rewrite an exponential, that would be an exponential form. All right, then if we solve it, 72 to the x power equals 1. And this is, again, where you have to kind of think through the process. So if we did 72 to the first power, that would be 72. So we know it's got to be something smaller than 1. And this is where we're just going to know. If you do anything to the 0 power, that's going to equal 1. So in that case, your x would have to equal 0. So if you did 72 to the 0 power, that would equal 1. So that means that in that case, x would wind up equal 0. Okay, so that's where if you're kind of going through these, sometimes it's good to have, that chart in front of you, or just a chart with any kind of positive and negative numbers to let you know that if you do something to the 0 power, that's always going to equal 1. That's kind of a big one that shows up a lot, that if you get something equal to 1, if you're rewriting this thing, then you automatically kind of know that that's going to be 0 that's going to be there. Okay, so we've got log of 3 base 9 equals x. All right, this one, the x is already here, so we're going to go ahead and rewrite it first. So we've got 9 to the x power equals 3. So again, take away the log, base stays the same, and just switch those two numbers. Okay, if you do 9 to the x power, well, if we do 9 to the first, we know that's going to be 9. Again, if we do 9 squared, that would be 81. So we can't get bigger. If we do 9 to the 0 power, that would be 1. 3 is somewhere in between those two answers. So our exponent's got to be somewhere between 0 and 1. And then people go, well, how do we figure out what that is? Because I don't know what that's going to be. All right, so here's what we've got to do. This is kind of the thought process you can go through on this one. What could we do? Now, again, take away, add, subtract, multiply, or divide. Forget about those for a minute. What could we do to 9? What operation could we do to 9 that would equal 3? That's not add, subtract, multiply, or divide. Not divide. Well, we said take divide off the board, but not something we could do to 9 that if we did this to 9, it would equal 3. Think about what we just got through doing on the last test there. Ooh, getting close. I think because when I say it, y'all gonna get it. This is something we could do to 9 that would give us an answer of 3. It's not add, subtract, multiply, divide. A different operation. Let's see. Where's it back here? Oh yeah, we were talking about it back here. What about one of those operations? Couldn't we square root 9, right? So if we took the square root of 9, that would equal 3. And people are like, well, what do we do then? Okay, so if that's the case, well, what do we do for that one? Here's what it is. Basically, square root is the same thing as a half power. So if you've got a number that's here, and here's kind of the way you can think about these when you go through it, is that it's because these are inverses. If we went backwards on this one, if we did 3 squared, that would equal 9. So they're like, okay, well, if 3 squared is equal 9, since we're putting the x over here, we've got to do the opposite of squared. So that means we've got to square root it. So that's kind of where they're going through on this one. So if you run across numbers where it's set up like that, where you're like, okay, the number's getting smaller, you've got to think about what you can do to get through it that way. So for this one, if we were solving it, then what are we here? This x would be to the 1/2 power. That would be our answer we're looking for. If we want to stick to the same kind of problem on that one, let's say we had to do log of 27 base, or log of 3 base 27. Okay, if we rewrite it, we've got 27 to the w power would equal 3. And again, the number is getting smaller. So if we did 27 to the first power, that would be 27. So we know we're not going to be at 1. We've got to be something a little bit less than 1. So we know we're at a fraction. Because again, if we did 27 to the 0 power, that would be 1. So again, it's still falling somewhere between 0 and 1. We can't square root 27 because that's not going to give you that one. So here's kind of what you have to think about it. Just go through your powers of 3. 3 to the first is 3. 3 squared is 9. 3 to the third would be 27. So if we did 3 to the w power, it'd be 3 to the third. Well, in this case, since we're kind of going backwards on this case, instead of it being a positive, instead of being a third like this one, this will make it a fraction. So w in this case would wind up being to the 1/3 power. It'd basically be like the third root of 27, if you want to think about it that way. So that's how you can kind of work these around. If you get the bases bigger than this number, you're going to have to do some fraction number to it. And the fraction number is kind of like going backwards. If you did this number to this power, then you can do 1 over that number to kind of get you there. So you have to kind of go a little bit of a backwards way to kind of get there. Give you one more of those, and I give you the other one that was kind of. There's one more. I was kind of hesitant on putting this one in the homework, but I did one problem just so we could kind of get there. Let's do log of 4, and 64 is the base. Okay, so if we rewrite it, it's 64 to the t power equals 4. And again, we know the base is bigger, so we know it's getting smaller. So there's where you kind of go backwards on it. 4 to the first would be 4. 4 squared is 16. 4 to the third would be 64. So again, if the t was over here, it would be 4 to the third. But since the t is over here, it's going to make it out to be the 1/3 power. Okay, so that's the one where it gets, you have to kind of think, again, the easy way to kind of or pick up on those is that your base is bigger than your answer that you get here. So if the base is bigger than the answer, and this is with your exponent up here, you've got to do some fraction answer to it. So it's like the square root or the half root or the third root, or how you want to look at it. It's just a different way to go at it there. Here's the one that's kind of I was kind of hesitant on this one. So we've got log of 25, or log of 125 base 25. They'll ask you to solve it, evaluate it, simplify it, something like that. So everything should be, I think, either evaluate or solve when we're going through these. All right, again, first thing is go ahead and just put that equal to X or T. Just pick some letter, you want to do M for Micah or A for Austin or, whatever you want to be. That's fine. The first thing is you want to rewrite it so it's 25 to the X power equals 125. So we take the log away, the base stays the same, we'll switch those two numbers. All right, here's the sneaky one on this one. Because if you do 25 to the first power, that's 25. If you do 25 squared, that is 625. And people go, well, okay, then how are we going to get there? Because if we do 25 to the first, that's 25. 25 squared is 625. So this number is somewhere between 1 and 2. How are we going to figure that out? All right, if you get one like this and there's no way you can figure out how to get from the bigger number to the smaller number, here's the one thing you've got to kind of catch on this one. 25, if you notice that one, that's 5 squared. And 25, you can make it 5 times 5. So that one, if they give you a number that's here, you can break it down and rewrite it as 5 squared. And then the X then just kind of stays with it there. Since the X was already an exponent, if you rewrite it as 5 squared, well, now the 2 and the X are together. All right, if we do powers of 5, then eventually we'll get to that one, because 5 to the first would be 5, 5 squared would be 25, 5 to the third would be 125, so then that would work, because this one didn't work doing the 25. Okay, so 5 to the third would equal 125. So then that means that the two X that's here has to be equal to the 3 that's here. So that means that X would then have to be equal to 3 over 2. Okay, if we did that as a decimal, that'd be 1.5, so that would put it in that range where it's somewhere in between those two. But I think they'll take to leave that one in fraction form. Okay, and that was one I was kind of back and forth on doing that one. I was like, okay, I'll put one of those in there that you've got to kind of get creative with that one. But there's only one like that. All the other ones will be like back here where you can either take the square root or cube root or something like that and find the answer. All right, and then the last one of the day. Last problem we've got to do. Let's say you've got log of X equals 2. Okay, and same thing. They'll ask you to either rewrite it or solve it or evaluate it, something along those lines. This one doesn't have a base. If there is no base, then it is understood to be base 10. So we'll make log X equals 2. Just go back and put a 10 right here. And then they'll tell you to, again, if they tell you to evaluate it or solve it, you're going to rewrite it without the log. So we're going to make it 10 to the second power equals X. In that case, it's really easy because 10 squared is just 100. So then X equals 100. Okay, so depending on how they give you the numbers, sometimes you've got to kind of think your way through like we were doing back here. In this problem, once we plugged in the numbers and reworked it, it was like, oh, well, there's the answer. It's just 10 squared, and then we go from there.